1999 Physics C, question 1. This was the first design your own experiment question that the AP asked. So let's look at it. Got just looking at this, I'm thinking there's going to be momentum and then energy, right? This is a ballistic pendulum. This is an inelastic collision here, and then it is a conservation of energy problem. But we have to do the inelastic collision separately from the conservation of energy problem because energy won't be conserved if that thing is sticking in there. But let's actually read it. Dart at M, fired, mass, length L, things are mass. Assume the size of the block is negative. Okay, whatever. The dart is moving horizontally. That's important. The block spins up there, and it becomes embedded in it. That's the important thing. Determine the speed of the dart immediately before it strikes the block. So I want to know what this V here is, right? So I'm going to do this in 2 stages. We're going to do from A to B to C. So we're going to work backwards here. And do the energy problem first. So this is my UG is equal to 0 line. And so from energy at C is equal to the energy at B, work non-conservative is equal to 0. That thing comes to rest. So that's mgy at C. We'll have to come up with an expression for that. It's equal to 1/2. Oh, and that M there is actually, we should say M plus M naught because they've stuck together. M plus M naught. Okay, it's going to cancel, so no big deal. The V at the B immediately after the collision squared, which is not what I care about. So those go away. There we go. And so I just need an expression for Y. Cool. So I know this is L, and that is L, that is theta. Okay, if I look here, I can talk about this length here, which is L cosine theta. Therefore, YC is L minus L cosine theta max. That is a very common geometry, so you should be comfortable with that. So I've got G, L minus L cosine theta max. We'll move the 2 over here, and the square root plus or minus. Get rid of that because it's just a speed, and that's the V at B. And now we'll do the momentum at A is equal to the momentum at B of the cis, because the net external force here is equal to 0. It's just the force of the dart on the block and the block on the dart. So initially I've got the V I want, so it's going to be the little m, because that's the mass of the dart, the V that I want. So I'm going to just call that V, capital V there, just to make it nice and simple, is equal to M plus M naught, and then that. So 2G, I'll pull out the L, 1 minus cosine theta max. Boom. And therefore, V is equal to little m plus that big M over little m square root of 2GL 1 minus cosine theta max. There we go. So that's the part A. It's a great little problem. So what else do they ask now? The dart and the block subsequently swing as a pendulum. Determine the tension of the cord when it returns to its lowest point. All right, actually, so we don't have to worry about the pendulum part because that's not on the exam, but we can actually do this problem here because that's just saying when it returns to its lowest point, it's going to have the speed that the block plus the dart had afterwards, so that VB there. And so tension, they're just making sure that you know how to do a sum of force in the radial direction. So that's tension minus, and the M here is little m plus big M is equal to little m plus big M. It's going to be that squared, so the square root of 2GL 1 minus cosine theta M, quantity squared over R, which is L. So I've got T is equal to, I forgot my G here, little m plus big M, quantity G is equal to, plus, because we moved over to the other side, little m plus big M. The L's are going to cancel, so that's 2G, and then 1 minus cosine theta M. Now, we could actually make that a little bit simpler because some of these terms will combine and whatnot, but they don't say you have to do it in simplest form. So that's my answer, and I'm moving on. Okay. So next, at your lab table, you only have the following equipment, right? Without destroying or disassembling any of the equipment, design another practical method for determining the speed of the dart just after it leaves the gun. Oh, okay. So here we go. Look at what I have here. I've got a spring. So I can do another type of ballistic pendulum, except that, so the idea here is, here's my dart. It's going to stick into a block, and there's a spring. What we're going to do is measure the compression of the spring. But first I need to know what the spring constant is. So find K, hang spring. We have a set of known masses, good. Hang spring, hang known masses, and let come to rest. Measure deflection from the natural length. And then graph F, or rather mg versus x, and the slope equals k. And then we're going to fire dart at block, measure the compression. Okay, and so this is going to be 1/2 mv squared, which is what I'm looking at, and it ends up being 1/2, we should say max compression, k, which we now know, x squared, boom, solved. And so that is how we would do it. We probably have to say here, measure compression, use conservation of energy to find v, which is going to equal k over m x squared square root. All right, and we know this, we now know this, and that's what we're measuring. So there we go. Right, developing an equation for what I'm looking for, and then figuring out a way to do it. I'm sure there's other ways of doing it, but that's my way of doing this problem.